Hello and welcome. You found your way to the Dream Scientist, where we gently unravel grand cosmic concepts, slowly and calmly, just soft enough to help you drift off. Whether you're unwinding after a busy day or simply curious about the universe from your comfy bed, I'm glad you're here. I truly hope this video isn't so captivating that it keeps you awake. But if it does, at least you'll wake up a little smarter than before. If you enjoy this calming science journey, I'd greatly appreciate a gentle tap on the like button, and perhaps even floating over to subscribe. It helps more curious minds like yours discover this channel. And while you're still awake, feel free to share where you're listening from and what time it is in your part of the world. I always love seeing how many corners of this spinning planet we reach. Now then, fluff your pillow, adjust your blanket, and settle in. We're about to explore the universe's natural curves together. Just a gentle reminder, this video is for educational and relaxation purposes only. It's not medical advice or a substitute for professional care. They say the shortest path between 2 points is a straight line. But in our universe, which is curved, coiled, and subtly complex, that idea rarely holds true. Even the most direct route, when followed far enough, begins to bend. A light beam curves as it passes a massive star. A migrating bird follows the arc of Earth's surface. A river left to itself meanders back and forth with a sort of peaceful perfection. All around us, the world seems to favor loops over lines, spirals over sharp angles, and gentle bends over direct routes. So, as you're settling in for the night, it's worth asking, do straight lines truly exist in nature, or are they just something we invented? Perhaps they're merely an ideal, existing more comfortably in our minds and mathematics than in the dirt, sky, or stars. In this video, we'll slowly walk through that question. We'll explore why the universe seems to curve almost everything it touches, why galaxies spin like vast hurricanes, why blood vessels weave through our bodies in branching arcs, why space itself, something we often imagine as flat and empty, bends under the weight of matter, folding time along with it. At the tiniest scales, particles seem to prefer dancing in clouds rather than marching in lines. This isn't just a story about shapes. It's about how the universe moves, grows, and breathes. It's about how life evolved to fit within a world that bends. It's about how geometry isn't just a rule book. It's a language, and it speaks in curves. There's no need to rush. We're not chasing definitive answers here. This journey isn't about memorizing facts or formulas. It's about gently drifting from one idea to the next, letting them settle like snowflakes or spiral like seeds. If you doze off somewhere along the way, that's perfectly fine. The curves will still be waiting when you wake up. So tonight we're stepping off the straight path. We're leaving behind our rulers, our right angles, and our grid lines. Stepping into a softer geometry, the kind that shapes galaxies and tree branches, blood vessels and orbits, light paths and time itself. Now let's see where the curves led. The straight line is one of humanity's most enduring inventions. You'll find it in ancient temples and modern skyscrapers, in the gridded streets of cities, and the ruled pages of notebooks. It's the foundation of blueprints, the guide for engineers, the mark of precision. We quietly revere it, perhaps without even realizing it. Every time we admire a neatly mowed lawn or a well-paved road, every time we connect to ideas and call it logic. But the truth is, the straight line is less a feature of nature and more a product of our imagination. Euclid, the ancient Greek mathematician, was one of the first to formalize it. He described the straight line as a boundless length, infinitely thin, extending forever in both directions, perfectly straight, perfectly smooth. It's a beautiful concept, clean, simple, reliable, but it exists in a world of thought, not in soil or sky. In the real world, things are messier. Try to find a truly straight line in nature, and you'll be searching for a while. Trees grow toward the sun in gentle arcs. Rivers wind and meander. Even the horizon, which looks flat at first glance, curves if you follow it far enough. Mountains bulge. Coastlines fray. Clouds billow. Nature rarely deals in sharp angles or unwavering paths. Still, we're drawn to straightness. There's something comforting about it, something efficient. Draw a straight road through a forest and you've imposed order on wilderness. Lay out a rectangular garden and you've tamed the wild into a pattern. Humans have always tried to straighten what was never straight to begin with. We carve tunnels through mountains instead of winding around them. We stretch bridges across rivers rather than letting the path follow the bank. We grid our cities, box our houses, frame our paintings. The more we build, the straighter our surroundings seem to become. Maps are a wonderful example of this. We flatten a round planet onto a sheet of paper and draw straight lines between destinations. But those lines are only straight in appearance. On the globe itself, the shortest path between 2 points is actually curved. It's called a great circle. Airplanes follow these arcs all the time, even though the line looks bent on a two-dimensional map. Our eyes see a curve, but the math says it's the shortest distance. Even the tools we use to define straightness are imperfect. A ruler? No. Matter how finely crafted, can warp over time. A laser pointer will eventually drift ever so slightly over long distances due to refraction or interference. The materials we build with wood, metal, stone expand and contract with temperature, moisture, and age. Nothing stays perfectly straight, not for long. In our minds, though, the straight line holds power. It represents clarity, purpose, and decisiveness. A straight line is a path with no hesitation. That's probably why we favor it so heavily. In design, straight lines look deliberate. They imply control. Architects use them to convey order. Graphic designers lean on them to create balance. Even language borrows the metaphor. Someone who tells the truth is said to be straightforward, while someone unreliable might be called crooked. But nature doesn't care about our metaphors. Nature, if anything, is playful. It curves not out of laziness, but because curves are often more efficient, more stable, and more adaptable. A straight tree branch snaps in the wind. A curved one bends and survives. Straight river cuts too deeply and too fast, eroding its banks. A curving river flows with less violence, spreading its energy gently. Curves distribute stress more evenly. They allow movement, growth, and resilience. Our brains, too, seem to prefer curves. Psychological studies have shown that people tend to find curved shapes more pleasing. It's more natural and even more calming than angular ones. One theory is that sharp angles can unconsciously trigger a sense of threat. After all, sharpness often means danger. Curves, on the other hand, feel safe. They're the shapes of rolling hills, rounded stones, and flowing water. They invite us in, rather than pushing us away. Still, we cling to straight lines. They help us measure, define, and build. They give us grids to navigate by, graphs to interpret, and frameworks to organize our thoughts. Without them, modern life would look very different. But in relying on them so heavily, we sometimes forget that they're only approximations. Zoom in close enough, and even a laser beam wobbles. Zoom out far enough, and even a highway starts too. Curve with the earth. The straight line is a tool, a useful one, no doubt, but it is not nature's native language. It's a translation, a simplification of a world that's far more fluid than we often admit. A world that doesn't march, but flows. That doesn't slice, but sways. It's a reminder that our best ideas, even the cleanest ones, are just that, ideas, models. Convenient ways to make sense of a universe that resists simplification. And perhaps that resistance is the most beautiful part. When you look up at the night sky, it's easy to imagine space as a vast, empty stage, a smooth, infinite canvas stretched flat in every direction. Planets and stars drifting quietly across it like actors in a slow-motion ballet. For centuries, that's more or less how people thought of space. Flat, passive, and quietly accommodating. But space, as it turns out, is anything but flat. It bends, it ripples, it warps, and stretches like a soft fabric under tension. And once you realize that, nothing in the universe quite looks the same. This idea, the shape of space, is one of the most quietly revolutionary insights in all of science. We owe it largely to Albert Einstein, whose general theory of relativity published in the early 20th century, changed our understanding of space from a rigid backdrop to a flexible participant in the universe's drama, according to Einstein. Gravity isn't a force pulling objects toward each other like invisible strings. Instead, it's the result of mass and energy bending the fabric of space-time. Picture a rubber sheet stretched tight. If you place a heavy bowling ball in the middle, the sheet sags under its weight. Now roll a marble across the surface. Instead of moving in a straight line, it arcs inward, caught by the dip created by the bowling ball. It's not that the marble is being pulled, simply following the curved shape of the sheet. In this metaphor, the rubber sheet is space-time. The bowling ball is a planet or a star, and the marble is another object, maybe a satellite or even a beam of light moving along the curves created by gravity. This is what Einstein proposed, that objects move not because they're pulled, but because they're following the geometry of space itself. It's a simple idea, and yet its consequences are profound. Gravity is no longer a mysterious force. It's geometry. And space is not the silent, still stage we once imagined. It's dynamic, responsive, and strangely alive. The Earth, for example, isn't being pulled into the sun like a rock on a rope. Instead, it's moving along a curved path in the sun's warped space-time. It's not that gravity reaches out and tugs the planet. It's that the Earth is falling around the sun endlessly, caught in the curvature created by the sun's mass like a marble forever, circling a funnel, never quite falling in, but never escaping either. This idea isn't just theoretical. It has been confirmed time and time again. One of the earliest pieces of evidence came in the form of starlight. During a solar eclipse in 1919, astronomers observed that stars appearing near the edge of the sun were slightly displaced from their expected positions. The reason? Their light had been bent as it passed through the sun's gravitational well. It was one of the first direct confirmations of Einstein's theory, and it caused quite a stir at the time. The headlines didn't hold back. Einstein had overthrown Newton. Of course, Newton wasn't exactly wrong. His laws still describe how gravity behaves in most situations, especially at everyday speeds and scales. But they didn't explain why gravity worked. Einstein did, in his version of the universe was curvier. To imagine space more accurately, it helps to think of it not as flat terrain, but more like an invisible fabric, something soft, elastic, and three-dimensional. Objects with mass sink into this fabric, creating dimples or wells that affect how other objects move nearby. The more massive the object, the deeper the well. A small rock barely dents the fabric. A planet makes a decent pit. A black hole? That's a bottomless tier. Even light, which travels at the fastest possible speed, is not immune to this bending. When a beam of light passes near a massive object, its path curves, not because it slows down, but because the space it's traveling through is curved. In a straight line through warped space, light ends up tracing an arc. This effect, known as gravitational lensing, allows astronomers to spot galaxies that lie behind other galaxies. The light bends around the foreground mass like water around a stone, and creates magnified, distorted images of things that would otherwise remain hidden. There's something poetic about that. Light, often our straightest symbol, our beam of truth and clarity, curved by the very fabric of existence. It reminds us that even our simplest metaphors have their limits. Another useful way to picture this is to imagine a ripple spreading across a pond. If the surface is smooth, the ripple moves evenly in all directions. But if there's a large stone sitting in the water, the ripple's shape will change as it flows around it. That's how space behaves when mass or energy is introduced. The presence of something heavy distorts the surrounding space, and anything moving through it, triples, marbles, planets, photons, follows the new curved geometry. Even time is part of this dance. According to general relativity, space and time are woven together into a single entity, space-time. When space bends, time bends with it. This is why time runs slightly faster on GPS satellites orbiting above the Earth than it does on the ground below. They're further from the planet's mass, sitting on a gentler slope in the gravitational well, and time ticks just a little differently up there. This isn't science fiction, it's science fact. Engineers have to account for these differences. when programming the satellite clocks, or else your directions to the grocery store could be off by several miles. All of this leads to a subtle but important realization. The universe doesn't operate on a flat playing field. Its rules are curved, its paths are bent, and its movements, when observed with precision, reveal the quiet elasticity of everything. Mass tells space how to curve, and space tells mass how to move. It's not a tug-of-war, it's choreography. Once you start to see it this way, it's hard to unsee. The planets are not merely spinning. They're tracing elegant arcs in a warped, invisible sea. Light is not beaming forward like a laser pointer in the dark. It is gliding through hills and valleys we cannot see. And space itself is not empty, sculpted, molded, and gently rippling under the weight of stars. In this curved universe, the idea of a perfectly straight path begins to look more like a myth than a measurement. And perhaps that's what makes it all so quietly astonishing. Even the emptiness bends. There's a certain elegance to the way things move in space. A moon circling a planet looping around a star gliding along the spiral arm of a galaxy. None of them travel in straight lines. Not for long, at least. Instead, they curve and turn and fall into paths shaped by the gentle pull of gravity. It might seem like an object moving through space should go straight, unless something gets in its way. That's not a bad instinct. It's part of what Isaac Newton realized centuries ago. He told us that an object in motion stays in motion in a straight line unless acted on by a force. But gravity is always acting, and that's where the curves begin. Imagine launching a cannonball off a cliff. Fire it gently and it falls nearby. Fire it harder and it travels farther before hitting the ground. But if you could launch it fast enough, the curve of its fall would match the curve of the Earth. It would never hit the ground. It would keep falling forever, but always just missing. That's what an orbit is, a controlled fall. The object isn't flying straight, it's curving around something, caught in a constant balance between its momentum and the gravity pulling it inward. This idea fascinated early astronomers. Johannes Kepler, working in the early 17th century, spent years studying the paths of planets. He discovered they didn't move in perfect circles as people had long assumed, but in ellipses, gently stretched loops. Each planet traces an oval path with the sun not at the center, but slightly off to the side, sitting at one of the two foci of the ellipse. This was a revelation. It showed that celestial motion wasn't based on ideal symmetry, but on a more flexible, accurate shape. Kepler didn't know why the planets moved this way. He simply described what he saw with mathematical precision. It wasn't until Newton came along that the deeper explanation emerged. Newton's law of universal gravitation explained how two objects attract each other with a force that decreases. With the square of the distance between them, combine that with his laws of motion, and suddenly Kepler's ellipses made perfect sense. The curve of a planet's orbit is the exact result of its speed and the gravitational tug of the star. Circles. If gravity were turned off, a planet would shoot off in a straight line, flying through space forever. But gravity holds it close, curving its path like a hand gently guiding a marble around the rim of a bowl. This balance between motion and pull is what allows orbits to exist, not just for planets, but for moons, satellites, and even spacecraft. The International Space Station, for example, isn't hovering over the Earth. It's falling around it again and again, traveling at over 17,000 miles per hour. There's nothing pushing it forward, simply coasting along its curved path, high enough and fast enough to stay in a graceful freefall. These curved motions aren't limited to neat loops either. Depending on speed and angle, an object can enter a wide variety of orbital paths, some tight and fast, others long and slow. A comet, for instance, might swing in from the outer reaches of the solar system, trace a stretched elliptical loop around the sun, and then drift back out for hundreds of years before returning. Still orbiting, but in a much more dramatic fashion. There are even hyperbolic and parabolic trajectories, curves that don't loop back at all. These are the paths taken by objects moving fast enough to escape a gravitational pull entirely. A spacecraft on a slingshot maneuver past a planet can follow one of these escape curves, using the planet's gravity to redirect its path without falling into a closed orbit. Again, it's not moving in a straight line. It's tracing a curved exit routes sculpted by the gravity it's slipping away from? Even within the apparent simplicity of an orbit, the path is rarely constant. The moon's orbit around the Earth wobbles slightly. The Earth's orbit around the sun changes shape over long time scales. These variations, called orbital perturbations, arise from the gravitational nudges of other bodies nearby. Jupiter, for instance, has a strong influence on the paths of many objects in the solar system simply because of its enormous mass. And then there's the fact that orbits don't happen in isolation. The moon orbits the Earth, which orbits the sun, which orbits the center of the Milky Way, which itself is being drawn slowly toward the Andromeda Galaxy. Everything is in motion. Nested curves within curves, a kind of cosmic choreography playing out across unimaginable distances. It's tempting to think of this as a kind of clockwork, a universe running on gears and loops. But that image misses something important. These motions aren't rigid. They aren't the result of fixed tracks or hidden wires. They arise naturally from the laws of physics, from the way gravity shapes the space around it, and from the way objects respond to that shaping. That's part of what makes curved motion in space so beautiful. It's not forced, it's graceful. A planet doesn't need steering. A moon doesn't need instructions. Their paths are written into the structure of the cosmos, inscribed not with ink, but with momentum and mass. Even our best efforts to simulate orbits, whether for satellites or missions to other planets, require incredible care and attention to tiny influences. A little too much thrust or a slight miscalculation of angle, and the result isn't a tidy ellipse. It's a missed target or a fiery plunge. The elegance of orbital motion comes not from its simplicity, but from its perfect balance. While it may seem counterintuitive, this balance always prefers curves. Straight lines are the exception, not the rule. They only appear when gravity lets go, and in a universe full of stars, planets, and invisible pulls that doesn't happen often. In the end, every orbit is a quiet agreement. The object wants to keep moving straight, but gravity gently insists otherwise. The result isn't a conflict, it's a dance. And that dance, endlessly varied and quietly precise, is one of the most beautiful expressions of curved motion we've ever discovered. In the quiet vacuum of space, movement is rarely what it seems. Objects glide effortlessly, their paths slow and serene from our distant perspective. But look closely, and you'll find a complex dance of curves unfolding. Nothing moves in a straight line for long, not because something stops it, because space is filled with invisible threads, tugging gently in all directions. Gravity, momentum, inertia, and time. And engineers, astronomers, and comets alike have learned how to ride those threads with elegance. One of the most brilliant examples of curved motion at work is the gravitational assist, also known as a slingshot maneuver.
Ow!
It sounds like science fiction. A spacecraft flies past a planet and somehow picks up speed without firing a single engine. But this is very real and very clever. Engineers use the gravity of planets not just to change a spacecraft's direction, but also to give it a boost, like a well-timed push on a swing. Here's how it works. Imagine throwing a ball toward a moving train. If you time it just right and the ball bounces off the front of the train, it leaves with more speed than it had going in. It gains energy from the train's motion. In space, the same principle applies. A spacecraft flies close to a planet, falls into its gravitational well, and swings around it. The planet loses an almost unnoticeable amount of momentum, and the spacecraft gains speed. It's a cosmic game of billiards, but with curves instead of straight shots. These assists are vital for reaching the outer planets and beyond. NASA sent the Voyager probes on their legendary journeys in the late 1970s. Mission planners lined up the planets like stepping stones. Each flyby added velocity and reshaped the trajectory. Without those slingshots, the spacecraft would have needed enormous amounts of fuel they simply didn't have. By embracing the natural curves of gravitational motion, engineers extended Voyager's reach from a few planets to the very edge of the solar system. What makes this even more poetic is that these maneuvers rely on precision within imperfection. Space is curved, gravity is subtle, and even a small miscalculation can send a spacecraft careening in the wrong direction. Yet when done right, it's a masterstroke of elegance, a curve within a curve, a fall that leads to flight. And this isn't just limited to probes. Satellites orbiting Earth also rely on curved motion to do their work. Many of them operate in elliptical orbits, dipping close to the planet at one end and swinging far out at the other. This variation in altitude isn't a mistake, it's a strategy. When a satellite moves closer to Earth, it speeds up. It climbs higher, it slows down. These changes in velocity help satellites spend more time over certain parts of the globe or sync up with specific times of day depending on their mission. Asterisk, asterisk. Then there's the wonderful trick of geostationary orbit, where a satellite moves in a circular path above the equator at just the right speed to match Earth's rotation. From our point of view on the ground, it appears to hover in place. It's zooming along at over 6,000 miles per hour, tracing a perfect curve in harmony with the planet below. A satellite on a straight path couldn't pull off that magic, it would simply drift away. It's the curve that holds it steady. Out in the darker reaches of the solar system, comets offer their own lessons in motion. These icy travelers spend most of their time in the distant cold, far beyond the orbit of Neptune, but every so often, gravity calls them inward. A comet will begin its long fall toward the sun, picking up speed as it approaches. It curves into a tight arc around our star, often glowing with a dramatic tail of vaporized gas and dust, and then slingshots back out into the void. These orbits can take centuries to complete. Halley's Comet, one of the most famous, visits us roughly every 76 years. Others, like Comet Hale-Bopp, may not return for thousands of years. Some, once they pass close to the sun, are flung onto new trajectories and never return at all. Their motion is governed entirely by curved geometry. No engines, no steering. Wheels, just mass and momentum tracing long frozen arcs through space. Watching a comet's path is like reading a signature from the universe. It reveals where it came from, how fast it's moving, and what gravitational encounters have nudged it along the way. Some comets have likely been shaped by ancient clothes. Calls with Jupiter or Saturn, which bent their orbits and redirected them into the inner solar system. Once again, the curve is not just an effect, it's the story. Even Earthbound missions have embraced these dynamics. When NASA sent the Parker Solar Probe to study the Sun, it didn't just aim straight for the target. That would have been far too dangerous. Instead, it used Venus again and again for gentle gravitational assists, slowly shrinking its orbit and curving closer to the Sun. With each pass, it's the spacefaring equivalent of gradually tightening a spiral. All of these movements assists orbits, returns. Escapes are only possible because of the way space bends under the influence of gravity. If space were truly flat and gravity acted in clean linear poles, none of these maneuvers would work. But the universe, thankfully, is more complicated and more graceful than that. This grace isn't just mathematical. It's visual, too. When we simulate these paths, what emerges are sweeping arcs, flower petal loops, and interwoven spirals. The trajectories of spacecraft often resemble calligraphy drawn at a planetary scale. There's something deeply satisfying about that. These are not brute force trajectories. They're carefully tuned partnerships with the natural motion of the cosmos, and all this from falling. That's the quiet truth behind it. Every satellite, every comet, every probe is just falling. But with exquisite timing and perfect curves, gravity doesn't shove. It invites, it guides. And in that guidance, things move not in lines, but in loops and swirls. In space, to move efficiently is to move beautifully. And the curve, again and again, is the most efficient shape of all. Look up at the night sky from a truly dark place, one without streetlights or car beams. Just you and the stars, and the universe reveals a depth that's easy to forget. Through a telescope, what looks like a faint smudge might turn out to be a spiral galaxy millions of light years away. Its delicate arms wrapped around a glowing core. These cosmic swirls aren't just beautiful. They're a signature, one of the most recognizable shapes in the cosmos. Spiral galaxies like our own Milky Way are everywhere. They make up a significant portion of all observed galaxies, and they tend to be the ones we notice first. There's something hypnotic about their shape, too. Maybe three sweeping arms coiled around a central bulge, like a giant pinwheel caught in slow motion. They appear orderly, elegant, and balanced. But underneath that graceful appearance lies a mystery that astronomers have been working to understand for decades. At first glance, you might expect that over time, the spiral structure would blur away. After all, if everything in a galaxy is rotating, wouldn't the stars closer to the center complete their orbits more quickly than those farther out? Think the arms would wind tighter and tighter until the entire thing resembled a disk of tangled string. Yet that's not what we see. The arms remain. The spiral pattern holds, not perfectly frozen, but remarkably persistent over millions, even billions of years. The answer to this puzzle lies in something called a density wave. A spiral galaxy isn't shaped like it is because its stars are glued in place, forming permanent arms. Instead, the arms are more like traffic jams. Imagine a busy highway where cars occasionally bunch up. The cars keep moving, but the clump, the jam, stays put longer than any individual vehicle. In a galaxy, the stars and gas clouds move through these higher density regions, which temporarily compress and brighten the material passing through. The result is a visible spiral pattern, not because the same stars are always there, but because the arms are zones of activity and motion. As gas clouds drift into these spiral arms, they get compressed, and that compression can trigger star formation. That's why the arms are often full of young, hot blue stars. They've recently ignited. Eventually, these stars drift onward. The gas moves along, and another region gets brightened in turn. The spiral, then, is less a structure and more a pattern, a wave of density rippling through the galaxy over time. And the whole system is rotating. Galaxies spin, though not like a record on a turntable. They spin differentially, meaning the inner regions rotate faster than the outer ones. This creates shear forces, stretching material along the spiral arms and helping to maintain their elongated form. It's a dynamic equilibrium, a shape that emerges and persists, not in spite of motion, but because of it. Now add another ingredient to the mix: dark matter. This invisible substance, which outweighs visible matter in galaxies by a significant margin, doesn't shine, doesn't absorb light, and doesn't interact with regular matter in any way we can easily detect except through gravity. That gravitational pull seems to be crucial in holding galaxies together. Without dark matter, the outer regions of spiral galaxies would rotate too quickly. The stars should be flung outward like water from a spinning sprinkler, but they don't. Instead, the rotation curves flatten out, suggesting there's more mass present than we can see. This hidden scaffolding of dark matter seems to stabilize the galaxy's overall structure, giving it the gravitational grip it needs to keep its stars from flying apart. All of this combines to create a form that's both stunning and surprisingly common. And what's fascinating is how often we find this spiral shape elsewhere in nature. Consider hurricanes. On Earth, these powerful storms form over warm oceans and begin to rotate due to the Coriolised effect. As they gather strength, bands of wind and cloud spiral inward toward a calm central eye. The resemblance to a spiral galaxy is striking, not just visually, but in terms of motion and energy. A system rotating, pulling in matter, releasing energy, and tracing a curve through fluid dynamics. Or look at sea currents. The swirling loops of ocean gyres, vast systems of circulating water, also echo this pattern. They move heat, nutrients, and currents across the planet, shaped by gravity, rotation, and the contours of the seafloor. Even in small, quiet places, the spiral shows up. The curl of a snail shell, the pattern of sunflower seeds, the swirl of milk in coffee. The spiral is nature's favorite rhythm, appearing at every scale from micro to macro. In galaxies, the spiral serves not just an aesthetic function, but a practical one. It organizes chaos. It encourages star formation. It redistributes energy and matter. It may even help regulate the growth and development of the galaxy itself. And while not all galaxies are spiral, there are ellipticals, irregulars, and lenticulars. Spiral type remains one of the most recognizable and photogenic of all cosmic structures. It's a kind of cosmic handwriting, a shape that says, here is movement. Here is gravity, inertia, time, and temperature, all playing together in a visible, comprehensible form. The fact that our own galaxy is one of these spirals makes the shape feel even more intimate. When we look at distant spirals in the sky, we're also looking at ourselves reflected in the grand architecture of the universe. Perhaps the most poetic part of all is that this shape, so vast and ancient, emerges naturally, doesn't need careful sculpting or a designer's blueprint. It arises from the quiet rules of physics, motion, gravity, pressure, and time, all curving together until a spiral blooms from stardust. When we imagine galaxies as pinwheels in the void, we're not far off, but the truth is even more beautiful. These swirls are not fixed, not static, but live in their own way, changing, shifting, spiraling forward in slow motion, a loop within. A loop, a pattern etched across millions of light years, repeating itself with elegant variation. The spiral, in the end, may be the universe's signature flourish, a gentle twist added to the raw mechanics of existence. And whether traced in cloud, sea, shell, or stars, it always feels like something alive. Nature has a particular fondness for curves, and nowhere is that more evident than in the subtle spiral shapes that crop up across the living world. From the elegant sweep of a ram's horn to the delicate coil of a pine cone and the pristine whirl of a nautilus shell, biology seems to have a favorite pattern, a spiral that grows but never loses its form. And at the heart of many of these shapes lies a quiet mathematical sequence, the Fibonacci numbers. If you have ever stared at a seashell and felt that strange sense of harmony, you're not imagining it. The logarithmic spiral, often associated with the Fibonacci sequence, is one of nature's most elegant tools. It's a shape that expands but keeps its proportions, curving outward endlessly without ever changing its overall appearance. This makes it ideal for things that need to grow while maintaining a functional and balanced design. Take the nautilus shell, for example. This ancient marine creature builds its shell chamber by chamber, always maintaining the same ratio between each new section and the last. The result is a spiral that looks the same, whether you zoom in or out, a perfect example of self-similarity. It's not just beautiful, it's efficient. The Nautilus gets a larger home without having to redesign its blueprint each time. The spiral handles the scaling automatically. The same principle applies to the horns of certain animals. Rams, goats, and antelopes often grow horns that curve in tight spiraling arcs. These aren't random. They follow geometric patterns optimized for strength and balance. A horn that simply stuck straight out would be brittle and prone to snapping. But a horn that coils distributes the stress of impact and grows in a way that remains centered around the animal's skull, helping it avoid toppling over. Spiral growth gives these creatures the tools they need to compete, defend, and survive, without sacrificing stability. And then there are pine cones, sunflowers, and even pineapples. If you look closely, you'll find a curious pattern in the way their seeds or scales are arranged. Often, they spiral outward in opposite directions. And if you count the number of spirals going one way and the number going the other, you'll usually find a pair of Fibonacci numbers 13 and 21. For instance, or 5 and 8. The Fibonacci sequence is simple. Start with 0 and 1, and then add the two previous numbers to get the next. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. It doesn't take long before the sequence starts showing up in strange places. The number of petals on many flowers, the branching of trees, the arrangement of leaves on a stem. Many of these follow Fibonacci patterns. Not because plants are doing math, but because these patterns maximize efficiency. In a sunflower, for instance, the seeds are packed as tightly as possible without wasting space. Spiraling them using Fibonacci ratios allows each seed to find its own spot, avoiding overlaps while filling the circular area completely. It's a natural form of packing efficiency. The plant doesn't need to calculate it. It just grows that way because those are the patterns that win out over generations. Evolution loves a good shortcut, and the spiral is one of its best. It offers strength, efficiency, and adaptability. Structures that grow in spirals tend to be mechanically stable and energy efficient. That's useful in countless biological contexts. From the microscopic curl of DNA molecules to the spiral pattern of a chameleon's tail when it coils around a branch, this doesn't mean that nature uses perfect mathematical spirals every time. Life is messy. What looks like a precise pattern up close often reveals little imperfections upon further inspection. But the underlying principles, the tendency towards self-similarity, the consistent proportions, the efficient use of space are remarkably consistent. Even our own bodies contain echoes of spiral logic. The cochlea in your inner ear, for example, is a tightly wound spiral structure responsible for turning vibrations into nerve signals that the brain can interpret as sound. Its spiral shape isn't just pretty. It's functionally brilliant. It allows a compact structure to sort different sound frequencies in a linear way, with higher frequencies detected near the base and lower ones near the apex. And if you've ever looked at the swirl on the back of your head or the fingerprint on your fingertip, you've seen tiny spirals written into your own biology. They're subtle, but they're a quiet nod to nature's recurring preference. The beauty of all this isn't just in the mathematics, but in the way these forms arise without planning. No flower is consulting a calculator. No ram is sculpting its horns according to a diagram. These spirals emerge because over time they work. They are what evolution leaves behind when it's looking for solutions to problems like growth, structure, and efficiency. There's something deeply calming about that. These spirals aren't the result of human ambition or artistic design. They come from basic rules playing out over time. A little pressure here, a little variation there, and suddenly the world is full of shapes that feel both familiar and mysterious. You don't have to know the Fibonacci sequence to appreciate the curl of a fern or the spiral of a galaxy. But once you do notice the pattern, it's hard to stop seeing it. It's in the way vines coil around poles. It's in the spiral staircase of certain shells. It's even in hurricanes and galaxies, though on a vastly different scale. What links them all is the quiet efficiency of the curve. Spirals are nature's way of growing without breaking, expanding without chaos, repeating without monotony. They allow for change without losing form, motion without confusion. Whether it's a ram charging headfirst into a rival or a sunflower quietly turning toward the sun, the spiral is there, guiding growth, shaping form, and whispering that nature doesn't need straight lines to find perfect solutions. It just needs time, a little pressure, and a touch of elegant mathematics. Inside your body, beneath the skin and muscle, there's an intricate landscape of curves. Arteries twist and turn like winding rivers. Veins loop gently back toward the heart, tiny bronchi branch and rebranch into an elaborate tree, carrying air to the deepest corners of your lungs. It's not a mess of tangled tubes. It's a carefully engineered network of paths that twist and arc for a reason. The curves aren't accidents. They're how life flows. When engineers design plumbing systems, they often prefer gentle bends to sharp turns. That's because sudden angles can create turbulence whirlpools and eddies that slow things down or cause damage over time. Your body follows the same principle. Every artery and vein is curved just enough to keep blood moving smoothly, reducing wear on vessel walls and preventing the kind of chaotic flow that can lead to clots or pressure imbalances. This preference for curves is deeply tied to fluid dynamics, the study of how liquids and gases move. In fluid systems, there are generally two kinds of flow: laminar and turbulent. Laminar flow is smooth, organized, and efficient. The liquid moves in parallel layers, gliding forward without much mixing between them. Turbulent flow, on the other hand, is chaotic. It involves eddies, swirls, and unpredictable shifts in pressure. While turbulence can be useful in some situations, like mixing chemicals, it's usually something to avoid in delicate systems, especially when those systems are responsible for keeping you alive. Curved blood vessels promote laminar flow. When the heart pumps blood into the arteries, it does so with considerable force. If the vessels were perfectly straight, the pressure would crash directly into the next segment, creating shock waves and stress. But with just the right curvature, that energy is diffused. The blood arcs gently around corners, guided instead of blasted. This reduces strain on the vessel walls and makes the system more durable over a lifetime of constant use. It also improves efficiency. Curved pathways allow the body to transport blood across long distances without requiring an enormous amount of pressure. Your aorta, the largest artery in the body, forms a gentle arch as it leaves the heart, bending elegantly before delivering blood to the rest of your organs. This isn't just because it looks nice on a diagram. That arch helps redirect the momentum of the heartbeat smoothly downward, reducing wear and tear while maintaining flow. The respiratory system follows a similar blueprint. Starting with the trachea, your airways branch and curve like an upside-down tree. Each time you breathe in, air flows through a system of narrowing tubes that split again and again, till they end in tiny air sacs called alveoli. This branching structure is known as a fractal one that repeats its shape at smaller and smaller scales. What's remarkable about this design is how much surface area it creates. Your lungs, when fully expanded, provide around 700 square feet of surface for gas exchange. That's roughly the size of a small apartment, folded delicately into your chest. And it's only possible because of the way the airways curve and divide. The curves in this system serve more than just space-saving purposes. They also slow the airflow at the right moments. As air moves deeper into the lungs, its speed decreases. This gives oxygen more time to pass through the thin walls of the alveoli and into the bloodstream. If the air rushed in too fast, it wouldn't have time to make the exchange. Curves act like ramps, easing the air into a gentler, more useful flow. There's also strength in curves. In engineering, a straight structure under pressure is more likely to buckle or snap, especially if the force comes from an unexpected angle. Curved structures distribute stress more evenly. That's why arches have been used in bridges for thousands of years. They're naturally strong. In the human body, curved vessels and tubes can expand and contract with changes in pressure without tearing. They offer flexibility and resilience, which is vital in a system that's always moving. Think of what your circulatory system deals with each day. Your heart beats more than 100,000 times, sending blood through more than 60,000 miles of vessels. That's enough tubing to circle the Earth twice and then some. A straight, rigid system would never survive that kind of demand, but one built on curves and flexibility, that system holds up, and it holds up quietly, without demanding attention. There's also an evolutionary advantage to this design. It's organisms that developed efficient, slow-stress circulatory systems were better equipped to survive, especially as they grew larger or more active. Fish, mammals, birds all have evolved looping, branching vessels that optimize flow and minimize damage. The curve once again wins. Even in the smallest details, the pattern repeats. Capillaries, the tiniest blood vessels, follow curved paths. Between cells delivering oxygen and nutrients where they're needed most, their winding roots ensure that no tissue is left too far from a source of supply. This redundancy is crucial. If one path is blocked, another can often take its place. And these systems are self-maintaining. Endothelial cells lining the blood. Vessels respond to flow. When the flow is laminar, they remain healthy. When it becomes turbulent, they can become inflamed or damaged. The body reacts by adjusting vessel diameter, rerouting flow, or triggering repair mechanisms. In this way, the shape of your vessels isn't fixed. It adapts ever so slightly over time to keep the flow smooth and the system resilient. It's worth pausing for a moment to appreciate just how much is happening beneath the surface. Every breath you take sends air through a spiraling network that adjusts for volume and pressure. Every beat of your heart drives blood through a curved system that's been shaped by millions of years of evolution to work efficiently and quietly. And all of it happens without your conscious involvement. You don't have to think about the geometry. Your body has already solved that problem elegantly. In the end, curves are not just about beauty or function. They're about survival. They make movement possible, reduce damage, and allow complex organisms to thrive. Straight lines may be quick, but they're brittle. Nature prefers to meander, to coil, to adapt. And in doing so, it builds systems that last a lifetime. When you breathe in, when your heart beats, when your blood flows, you're living inside a masterpiece of curved design of flowing. Branching, resilient network, shaped by the quiet logic of motion. It's a soft-spoken miracle that works in spirals and arcs, never shouting, never rushing, just flowing forward, one gentle bend at a time. All around us, nature draws in branches. A tree stretching toward the sky, a river carving its way to the sea, a flash of lightning racing toward the ground. Each one follows a pattern that feels both spontaneous and intentional. At first glance, they might seem random, a chaotic mess of forks and forks within forks. But look more closely, and a quiet order begins to emerge. These patterns are not chaotic at all. They are precise, repeating, and astonishingly efficient. Consider a tree. From the trunk, thick branches grow outward and upward. Those branches split into thinner ones, which split again and again until they end in tiny twigs and delicate leaves. This isn't just a matter of growing outward. It's a system designed for delivery, getting sunlight to leaves, moving water from roots to canopy, and resisting the wind without breaking. The structure must be strong but flexible, broad yet light. Every fork in the pattern balances these needs. But trees aren't the only things that branch like this. Rivers do too. A river often starts as a small trickle high in the hills. That trickle is fed by smaller flows, which are themselves fed by even smaller ones. As the water moves downhill, the channels join and rejoin, forming a dendritic network, a word that comes from the Greek word for tree. A river basin viewed from above looks remarkably like the branches of an oak or maple, just flattened onto a different plane. Then there's lightning. When electrical charge builds up in a cloud and searches for a path to the ground, it doesn't take a straight shot. Instead, it forks and splits, probing in multiple asterisk directions at once. Some of these paths meet obstacles, air resistance, competing charges, and terminate. Others continue. Eventually, one path finds its way to the ground, and the main bolt follows that pre-carved channel. The flash you see is just the final surge, lighting up the maze of decisions that preceded it. In all of these examples, the branching isn't a design imposed from the outside. It emerges naturally from simple rules. The tree branches to maximize light and minimize weight. The river branches to follow gravity while navigating the terrain. The lightning branches as it seeks the path of least resistance through the air. Different forces, different materials, but the shapes that result look strikingly similar. This similarity is more than a coincidence. It's a feature of what scientists call fractals, patterns that repeat at different scales. A small branch looks like a bigger one. A tiny stream resembles the larger river it feeds into. Even a small segment of a lightning bolt has the same jagged character as the whole strike. These patterns are self-similar, meaning they carry the same basic structure no matter how far you zoom in or out. Fractals are nature's way of solving complex problems with elegant simplicity. Want to cover a lot of surface area without using too much material? Branch? Need to distribute nutrients or drain water or carry energy across a space? Branch again. Keep dividing, keep narrowing, and the pattern grows naturally into something both efficient and resilient. This approach shows up everywhere in biology, not just in trees, but in lungs, blood vessels, and the nervous system. The bronchial tree inside your chest branches roughly 23 times from the trachea to the alveoli. Each division increases the surface area available for gas exchange while keeping the entire system compact enough to fit inside your rib cage. It's an architectural marvel built from nothing more than repetition and curves. Even coral reefs, fungi, and neurons follow similar patterns. These organisms, though wildly different, all face the same fundamental challenge: how to expand, connect, and distribute. Branching solves the problem in every case. It's like a universal blueprint for complexity. And it turns out the curves in these systems aren't just functional, they're also optimized. Nature doesn't branch wildly just for the fun of it, there's math behind it. Researchers have found that the angles at which branches split often follow principles that balance energy and material use. In river networks, for instance, the spacing between tributaries tends to follow scaling laws that reduce erosion and spread flow evenly.
Ow.
In trees, the branching angles are often just right to distribute leaves without overcrowding. Even lightning follows statistical patterns that physicists can model with surprising accuracy. What looks random is actually a delicate compromise between competing needs: strength versus flexibility, reach versus economy, speed versus precision. A lightning bolt could, in theory, go straight down, but doing so would increase resistance and decrease its odds of success. A tree could grow one giant leaf, but that would collapse under its own weight and block its own sunlight. Instead, nature splits the difference again and again into forks, arcs, and spirals. These branching systems also allow for redundancy. If one limb breaks, another can take over. If one stream dries up, others can shift to compensate. Of resilience is a hallmark of natural design. It's not about perfection, it's about adaptability. And curves, with their ability to bend rather than break, play a vital role in that adaptability. Interestingly, our own designs often borrow from these patterns, sometimes intentionally, sometimes instinctively. Road systems, power grids, and internet cables often follow branching layouts, especially when trying to reach a wide area efficiently. But we tend to lean more heavily on rigid symmetry than nature does. Our branches are straighter, our angles sharper. Nature, on the other hand, prefers just enough irregularity to keep things stable. It allows for gentle curves, asymmetry, and a little bit of chaos. That small departure from uniformity is often what makes the system work. There's also a psychological element to these shapes. Studies have shown that people find fractal patterns calming, especially those that resemble natural forms. Walk through a forest or gaze at river deltas from above, and you're looking at a world organized by rules you don't consciously know, but which your brain seems to recognize anyway. Maybe that's part of why these patterns feel so satisfying. They're not just efficient, they're familiar, even comforting. All of this points to a deeper idea. Nature doesn't design in the way a human would, with sketches and measurements. It evolves, iterates, and adjusts over time. The shapes that work are the ones that survive. And again, those shapes are curved, branching, and quietly mathematical. From the tallest trees to the flash of a storm, from trickling streams to the synapses in your brain, the pattern repeats. Not because nature is copying itself, but because the same rules keep applying. Energy flows more easily when it curves. Materials stretch further when they branch. Systems survive longer when they spread and divide. It's a kind of gentle genius, a reminder that the world doesn't need straight lines to be beautifully ordered. It just needs enough room to branch. Light, for all its speed and sharpness, is not as straight as it seems. It zips along at nearly 300,000 kilometers per second in a vacuum. And yet, even at that unthinkable pace, its path can bend. Not because it wants to, of course light has no preferences, but because the world it travels through bends it. You can see this bending in the simplest of places. Dip a straw into a glass of water and observe how it suddenly seems to snap or kink where it enters the liquid. What you're seeing is refraction, the bending of light as it passes from one medium to another, in this case, from air into water. The light rays slowed down just a little when they enter the denser medium, and that change in speed alters their direction. The result is a visual illusion, but it's not trickery. It's geometry. The same principle governs eyeglasses, cameras, and telescopes. Lenses are curved precisely to bend light in predictable ways, either to bring it into focus, spread it out, correct how it's entering your eye. A convex lens, for example, gathers light and bends it inward to form a single focal point. A concave lens spreads light outward. All of this works because light responds to the contours of the materials it moves through. The curvature of the lens decides how the light will travel, much like a riverbed decides how water will flow. And while a lens is a carefully crafted curve, the world offers plenty of natural lenses too. Air, for instance, can bend light just as water or glass can. Layers of warm and cool air refract light differently, and under the right conditions, this can produce stunning optical illusions. One of the most well-known is the mirage.
Imagine
Walking across a hot road on a summer day and seeing what looks like a pool of water shimmering ahead. It's not actually there. Your brain is misreading bent light. The sun heats the road, which warms the air just above it. Its hot layer of air bends light rays upward, so when you look down the road, your eyes receive light that has taken a detour. Your brain, ever helpful, interprets it as a reflection. The result is a ghostly puddle floating in a heat haze. In the desert, this effect can be even more dramatic, creating images of distant landscapes that seem to hover in the sky. These superior mirages occur when cooler air sits beneath a warmer layer, bending light downward instead of up. It's a reminder that our sense of direction is only as straight as the light that reaches us, and that light loves a curve. Asterisk, asterisk. Then there are rainbows. These cheerful arcs painted across the sky are the result of sunlight entering countless raindrops, bending and reflecting within them and exiting at just the right angle. Each droplet acts like a tiny prism, breaking white light into its component colors. But the curved shape of the rainbow isn't a product of the droplets themselves. It's a consequence of geometry. The light that exits each raindrop and reaches your eyes does so at a very specific angle, about 42 degrees from the direction opposite the sun. Because of that fixed angle, the rainbow appears as a circle, or at least the visible arc of one. If you were in an airplane above the rain, you might even see the full circle. The halo around the sun or moon follows a similar principle. It's created when light passes through ice crystals high in the atmosphere. These crystals are often hexagonal, and when light hits them just right, it refracts and forms a ring at a specific angle, often 22 degrees. Once again, the light is bent, not in a chaotic way, but in accordance with its surroundings. The curve isn't added, it's revealed. Even shadows, which we often imagine as crisp and straight-edged, carry the fingerprints of curvature. The edges of shadows blur because light comes from a source with size not a single point, but a disk. The sun, for instance, is large enough that light from its different edges arrives at slightly different angles. This softens the boundary between shadow and light, creating a gradient known as the penumbra. When the moon eclipses the sun, or the earth casts a shadow across the moon, the curved edges of those shadows reveal the roundness of the objects involved. And then, of course, there's gravity, the grandest lens of all. As Einstein predicted in his general theory of relativity, light doesn't just bend when it changes medium. It also bends in response to mass. A massive object like a star or a black hole warps the fabric of space-time around it. Light, always trying to travel in the straightest possible path, ends up following a curve through that bent space. The result is gravitational lensing, a kind of cosmic magnifying glass. When we observe galaxies through the gravitational field of something massive in the foreground, we often see arcs, rings, and distorted images of the more distant light source. These Einstein rings, as they're sometimes called, are dramatic. Evidence that light, though fast, is not immune to influence. The path it travels depends on the shape of the universe it moves through. This effect allows astronomers to see things that would otherwise be hidden distant galaxies to faint to detect directly, with the presence of invisible dark matter that reveals itself only through the way it bends, passing light. In a way, these cosmic curves give us a glimpse into what's otherwise unreachable. What all these examples have in common lenses, mirages, halos, and gravitational arcs is the same. Quiet lesson: light does not insist on moving in a straight line. It takes the path available, and that path is almost always curved by something, be it glass, water, air, or gravity itself. Even your eye is a curved structure designed to focus light onto the retina, yet the curve is too steep or too shallow. You see the world out of focus. The act of seeing is built on bending. Vision, in a literal sense, depends on light changing course. It's easy to think of light as sharp and linear, like the beam of a flashlight in the dark. But in practice, it flows. It refracts, reflects, spreads, and loops. The way it moves is deeply sensitive to its environment, which is rarely uniform. Light bends because the universe is uneven, layered, lumpy, in motion. The geometry of the world guides it. In all of this, what appears to be a simple line is often a dance of detours. A ray of sunshine traveling through the atmosphere is bent a little by air, scattered by particles, bent again by a droplet, then split into color, and finally curved once more by the curvature of your own lens before becoming an image in your mind. That's a long journey for something we usually take for granted. And yet, because of these gentle deviations, we see rainbows, halos, sunsets, and stars warped by invisible forces. The beauty lies not in light's refusal to bend, but in the countless wonders that arise when it does. Take a globe, wrap a string around it from New York to Tokyo, and pull it tight. You'll see that the string arches upward toward the Arctic, forming a gentle curve. Now open a flat map and draw that same line. It looks like a strange detour. You might wonder, do planes fly such an odd route? They don't. They fly the shortest path. It just doesn't look that way on a flat surface. Welcome to the curious geometry of Earth's the round world that doesn't play by two-dimensional rules. Our planet is a sphere, or very close to one, slightly flattened at the poles and bulging a little at the equator. And on a sphere, the shortest path between 2 points is not a straight line, but something called a great circle. Imagine slicing the Earth into 2 equal halves with a perfectly flat plane. That slice is a great circle. The equator is one, and so is any line that wraps around the globe and passes through its center. Airplanes follow great circles whenever possible. That's why flights from North America to Asia often curve far north, flying over Alaska or Siberia. It looks inefficient when you view it on a flat map. But from the airplane's perspective, it's the quickest way between 2 points. Less fuel, less time, and fewer miles. The arc is an illusion of perspective. In reality, it's a geodesic Earth's version of a straight line. Our brains aren't naturally wired for spherical geometry. Most of the maps we grow up with are flat rectangles. They're easy to print, stack, and hang on walls. But turning a sphere into a flat surface always involves distortion. There's no perfect way to do it. One of the most common projections is the Mercator map, invented in the 16th century for navigation. It preserves straight compass bearings, which is useful for sailors, but it warps size and shape, especially near the poles. That's why Greenland looks enormous, almost the size of Africa, even though Africa is over 14 times larger in reality.
Oh.
On this projection, the poles stretch toward infinity, and great circles turn into bowed, looping curves.
Ow.
Other projections try to fix these problems. The Robinson projection smooths things out to give a more accurate sense of scale. The Winkle triple tries to balance area, shape, and direction. The good Homolocene map cuts and splices the globe like an orange peel. To preserve landmass proportions, each method solves some problems and creates others. No matter what, you're sacrificing something: distance, angle, shape, or area. And yet, we treat flat maps as though they perfectly represent the world. We use them for planning road trips, tracing flight paths, and learning geography. But that mental flattening hides some strange truths about travel and perspective. One of the most surprising, the fact that what appears to be a longer, curved route may actually be shorter than a straight-looking one. This comes into play in countless real-world applications. Submarine cables that stretch across oceans follow great circles, not straight lines. And migrating birds often use curved routes that seem indirect but save energy. Even GPS systems must calculate distances using spherical trigonometry to give us accurate directions. Consider this: if you were to walk from point A to point B in a perfectly straight line while remaining at sea level, you'd still be tracing a subtle arc along Earth's surface. The ground beneath you curves ever so slightly, even if you can't feel it. If you truly walked in a straight line, ignoring gravity entirely, you'd slowly rise into the sky, eventually leaving the surface altogether. Straight lines and curved surfaces don't get along. Asterisk, asterisk. Well, this is one reason why surveying long distances requires careful math. When engineers build roads, tunnels, or pipelines that stretch for miles, they have to account for Earth's curvature. A laser shot straight across a flat landscape over a long distance will end up floating above the ground because the land gently curves away beneath it. It's a small difference, only about 8 inches over the first mile, but it adds up quickly. The curve of Earth also affects how we see the world around us. Ships vanish hull first over the horizon, not because they're sinking, but because they're following the curve of the planet. Sunsets and sunrises are delayed or hastened, depending on your elevation. Climb a mountain, and the sun sets later, because your perspective has shifted over the roundness of the Earth. Astronauts in low Earth orbit see the entire planet as a glowing blue marble wrapped in atmosphere and shadow a perspective that neatly erases the notion of flatness. Even the horizon itself is curved, though our eyes rarely notice. On a clear day at sea, with a wide view and a calm mind, you might detect the slightest arch. But for most of us, the illusion of flatness dominates. We navigate in straight lines on a curved world and rarely question the mismatch. There's a gentle poetry in that. We build our grids and roads, our cities and maps, with right angles and linear edges. But underneath all of it lies a softly curving Earth, always rounding away beneath our feet. The structures we erect, skyscrapers, bridges, towers, are technically not parallel at their tops. If extended upward forever, they'd eventually meet at Earth's center. Building ever so slightly leans away from its neighbor. This isn't just a curiosity. It's a quiet reminder that our systems and symbols maps, rulers, paths are approximations. Useful? Yes, but simplified. The truth is round and it bends. To travel the shortest distance between two faraway cities, we must abandon what looks straight. We must arc across the globe. Trust the mathematics and let our paths rise and fall with the planet. It's a metaphor hiding in plain sight. When you fly from Los Angeles to London and find yourself halfway over Greenland, it's not a detour. It's the Earth guiding you along its true curve. And in that curve, there's efficiency, wisdom, and a quiet elegance. Nature, once again, favors the arc over the angle, the loop over the line. What appears to be crooked is often correct. What looks inefficient may be the most direct. And in a world that insists on curves, perhaps the most important journeys are the ones that bend a little along the way. Time, like space, once seemed like the kind of thing that should behave. We imagined it as steady, dependable, ticking along. At the same rate, everywhere in the universe, like a cosmic metronome. And for centuries, that worked just fine. Clocks kept time. Calendars marched forward. Moments stacked neatly into days and years. Time was background noise, reliable, invisible, and flat. Then Einstein came along and bent it. In the early 20th century, Albert Einstein published his general theory of relativity, a sweeping reimagining of how gravity works. Rather than viewing gravity as a force pulling objects toward each other, he described it as the curvature of spacetime. Energy, he said, warp the fabric of reality and objects, including you and me. Simply follow the paths carved into that fabric. It was already a radical idea that space itself could bend. But time? That was something even stranger. According to general relativity, time is not separate from space. It's part of a four-dimensional continuum called spacetime. And just like space, time is affected by gravity. The stronger the gravitational field, the slower time runs. This isn't just a philosophical idea. It's measurable, testable, and very real. If you place two identical atomic clocks, one on the ground and one at the top of a mountain, they would eventually tick at different rates. The clock higher up, farther from Earth's center of gravity, would tick just a little faster than the one closer to the surface. The difference is minuscule, just billionths of a second, but it's there. Gravity doesn't just pull on your feet, it pulls on your seconds. In day-to-day life, you don't notice this effect. But when precision, matters, say in the world of satellites and global positioning, it becomes impossible to ignore. Your phone's GPS works by receiving signals from satellites orbiting about 20,000 kilometers above Earth. These satellites each carry atomic clocks and broadcast the exact time continuously. Your phone calculates how long those signals take to reach you, compares data from multiple satellites, and triangulates your position. Here's where things get tricky. Because those satellites are moving quickly and are located far above the Earth's surface, two time-altering effects come into play. First, due to special relativity, their high speed causes their clocks to tick slightly slower than ours. Simultaneously, because they're farther from the planet's gravitational pull, general relativity causes their clocks to tick faster. The net result? GPS satellite clocks run faster than ground clocks by about 38 microseconds per day. That might not sound like much, but if uncorrected, that tiny drift would throw off your position by several kilometers within a single day. Your phone would think you were somewhere completely different. The entire navigation system would crumble. To make it work, engineers have to build these relativistic corrections into the software. Every time you get directions to the nearest coffee shop, you're using Einstein's equations. It's a quiet, astonishing fact. Modern technology depends on the curvature of time. And this curvature doesn't stop with satellites. It gets even stranger near massive objects. The stronger the gravity, the more time slows down. Near a black hole, time can slow to an extreme degree. If you were to orbit close to one without falling in, time would pass much more slowly for you than for someone watching from a safer distance. Spend an hour near the event horizon, and years might pass elsewhere. This isn't theoretical fantasy. It's baked into the math and supported by observation. The implication is wild. Time is not universal. It's local. It stretches and compresses depending on where you are and how fast you're moving. There is no master clock ticking behind the scenes. Each location in the universe experiences time at its own pace, shaped by gravity and motion. In our everyday experience, time feels absolute. But that's only because we're all moving through a fairly uniform gravitational field. Once you step outside that comfort zone into orbit, into deep space, or close to something massive, the differences emerge. They're subtle at first, but they scale dramatically with mass and speed. Einstein's insight also means that space and time are linked in ways we can't always visualize easily. Move through space quickly, and you experience less time. Sit still near something heavy, and your time stretches out. It's as if every point in the universe has its own tempo, a rhythm dictated not by a universal beat, but by mass and motion. Gravity doesn't just curve space, it changes the way events unfold. If that seems hard to wrap your head around, you're in good company. Even Einstein reportedly found the implications of his own work unsettling. The idea that your heartbeat could be tied to altitude, that your minutes depend on momentum, or that a path through time is shaped like a spiral rather than a line that's enough to twist the mind. But there's something beautiful in it too. It means the universe is not built on rigid frameworks, but on relationships. The way you experience time is deeply personal, on in the emotional sense, but in the gravitational one. The shape of the world around you is sculpting the seconds you live. This becomes especially profound when you realize that the passage of time isn't just an effect of space, it also helps define what space is. The two are inseparable. Bending of asterisk, asterisk, asterisk. One alters the other. In a way, when we talk about the geometry of the universe, we're really talking about the geometry of experiences, the paths that matter and light can take, and how long those journeys feel. None of this means time is an illusion. Far from it. It's just more flexible than we thought. Like light, like space, it bends. And in those bends are secrets that GPS satellites whisper, that black holes roar, and that quiet mountain clocks quietly echo as they tick ever so slightly faster than their sea-level twins. We live in a world where gravity isn't just pulling on us. It's reshaping our passage through time itself. It's a reminder that reality is layered, textured, curved not just in space, but in the unfolding of every moment. March. It flows. It loops and leans and stretches. And understanding that curve doesn't make time any less mysterious, it simply makes it more marvelous. Down at the smallest scales of reality, the universe starts to behave in ways that defy common sense. Objects blur into clouds. Movement becomes a matter of probabilities. The tidy paths we imagine at predictable lines begin to dissolve into shimmering uncertainty. Welcome to the quantum world, where nothing, not even a particle, seems to travel in a straight line. Take the electron, for instance. In early models of the atom, electrons were imagined as tiny balls orbiting the nucleus like planets around the sun. It was a simple, satisfying picture, each electron following a neat circular track. But as physicists dug deeper, that model began to unravel. Electrons don't travel in little loops. In fact, they don't really travel in well-defined paths at all. Instead, an electron exists as a kind of probability cloud. You can't say exactly where it is, only where it's most likely to be. The more precisely you try to pin down its position, the less you can know about its momentum, and vice versa. This is not just a matter of limited technology or measurement error. It's baked into the nature of reality. Heisenberg's uncertainty principle tells us that at the quantum level, precision has limits. You can't draw a clear trajectory, because there isn't one. The electron doesn't move from point A to point B along a clean, straight road. It flickers between possibilities, smeared across space like a whisper of probability. To visualize it, think of a hummingbird darting through fog. You might catch a glimpse of it here and there, but you can't trace its exact path. And unlike the hummingbird, the electron doesn't leave a trail. It exists in a haze of where it could be, and only collapses into a specific location when observed. This fuzzy behavior shows up dramatically in the famous double-slit experiment. Fire particles like electrons or photons one at a time through a pair of slits, and you'd expect them to land behind one slit or the other, right? Like tiny bullets. But what you get instead is an interference pattern, a series of light and dark bands, as if each particle interferes with itself, as if it behaves not like a marble, but like a wave that goes through both slits at once. And here's the twist. The moment you try to measure which slit the particle goes through, the interference pattern vanishes. It starts behaving like a particle again. Observation changes the outcome. The straight path once again proves elusive. What we thought was a point becomes a wiggle. What we thought was a line becomes a cloud of maybes. This wave-particle duality is at the heart of quantum physics. Particles aren't really particles. Waves aren't just waves. They're both and neither, depending on how you look. It's as if the universe keeps its options open until someone insists on an answer. And even then, the answer feels more like a suggestion than a certainty. This behavior isn't limited to electrons. Photons, neutrons, even atoms and molecules have shown similar patterns in carefully controlled experiments. The bigger the object, the harder it is to maintain that quantum weirdness. But the principle still holds. Straight-line trajectories at the smallest scales dissolve into curved probabilities. Then it's not just a theoretical curiosity. Quantum mechanics underpins everything from lasers to computers to the GPS in your phone. The behavior of electrons in probability clouds determines how atoms bond, how electricity flows, and how the chemistry of life unfolds. All of it emerges from particles that refuse to move in predictable lines. Even in systems where particles appear to be confined, like electrons in an atom, they don't orbit in neat circles. Instead, they inhabit orbitals strange three-dimensional regions with complex shapes, spheres, dumbbells, rings, and more. These are not the paths of the electrons, but regions where they are most likely to be found, a kind of blurred choreography, elegant in form, but impossible to trace. And within this randomness lies a deeper order. The probabilities themselves follow precise mathematical rules. Schrödinger's equation, the foundation of quantum wave mechanics, doesn't predict where a particle is, but it tells you how the cloud of possibility evolves over time. The curves may be fuzzy, but they are still curves, governed by equations that ripple through the fabric of reality. This curving behavior becomes even more dramatic when you consider phenomena like quantum tunneling. Imagine a ball rolling toward a hill that it doesn't have enough energy to climb. In classical physics, it would simply bounce off and roll back down. But in the quantum world, there's a chance. however small, that the particle will appear. On the other side of the barrier, without ever crossing it in the normal way, it tunnels through, not in a straight shot, but via probability, as if the particle took a route that only exists in potential, not in space. This is how the sun shines. Fusion inside the sun's core depends on particles tunneling through energy. Barriers. Without quantum curves and wiggles, our star wouldn't work. Life itself wouldn't exist. So, the refusal of particles to travel straight isn't just a quirk, it's essential. The universe is built from movement that bends, from possibilities that ripple, from actions that don't obey linear thinking. The quantum world is a landscape of gentle uncertainty, where certainty itself is the outlier. Even time behaves oddly. Down here. Quantum entanglement, the phenomenon where two particles share information instantly over vast distances, seems to ignore conventional timelines. Cause and effect blur. Measurement becomes part of the event, path forward rather. Then being a straight arrow becomes a branching tree of maybes. And yet, out of this curved chaos emerges the solid, predictable world we see. Chairs don't shimmer. Apples don't tunnel through tables. But beneath that stability is a churning sea of curved probabilities. A foundation of gentle chaos where straightness is only ever an illusion of scale. At the smallest levels, the straight line doesn't survive. It's not because something pushes it off course, but because the concept of course itself begins to unravel. There's no tiny billiard ball clicking its way through the cosmos, only clouds. Only patterns, only curves. The deeper we look, the more we find that certainty fades and elegance rises in its place. Not the rigid elegance of straight edges, but the softer elegance of fluctuation, possibility, and flow. Even the simplest particle, when left alone, chooses not to march, but to wiggle. In a universe built from uncertainty, perhaps the most natural thing is to embrace the curve, to accept that even the smallest journeys wander. Nature rarely draws in straight lines. It loops, curls, and arcs with a grace that feels almost intentional. But it's not artistry, it's evolution. Over countless generations, life has learned that curves aren't just beautiful. They're practical, efficient, and quietly brilliant. Evolution favors what works, and what works more often than not is curved. Take a look at a snail shell. That perfect spiral coiled tightly from a central point isn't just for decoration. It's a compact and highly efficient asterisk, asterisk, asterisk way to grow. As the snail matures, its shell expands outward in a logarithmic spiral, meaning it grows but never changes shape. The snail doesn't have to rebuild its home. It just adds to it. The result is stability without waste, strength. Without weight, a soft, smooth geometry that stands up to pressure while protecting its squishy resident. This kind of curve isn't limited to snails. You can find similar spirals in the horns of rams, the tusks of narwhals, the tails of seahorses, and the swirling seeds of sunflowers. Curves show up again and again in the natural world, not because they look nice, but because they solve problems. Curved claws, for example, give animals better grip and leverage. A hawk's talon is a beautifully honed hook designed to pierce and hold. A cat's claw retracts in a gentle curve, staying sharp and ready. These arcs create mechanical advantage. They concentrate force, reduce stress, and hold tight. Like straight claws don't catch nearly as well. Tails too often bend for a reason. Think of a chameleon's prehensile tail. It curls like a fifth limb, helping the animal stay balanced as it tiptoes through treetops. The tail wraps around branches, grips like a spiral spring, and moves with quiet elegance. It's not just a decoration. It's a survival tool shaped by millions of years of subtle tweaks. And it works better curled than straight. Even our own bodies are full of curves that serve a purpose. The arches in our feet distribute weight and absorb shock as we walk. The curve of our spine helps us stay upright while keeping flexibility. Our ribs bend around our lungs, not just for protection, but to expand and contract with breath. Our very DNA is a double helix, a twisted ladder of genetic code. If life had a favorite shape, it might just be the spiral. Why do curves work so? Well, one reason is efficiency. A curved structure often requires less material to achieve the same strength as a straight one. Domes, arches, and spheres distribute stress evenly. That's why you see curved bones in bird wings, coiled shells in the sea, and dome-like skulls in mammals. Nature, much like a clever architect, avoids sharp corners whenever possible. Straight lines can be brittle. They create points where stress builds up, leading to cracks or breaks. Curves, by contrast, allow forces to flow smoothly. Water moves more easily through a curved channel than a sharp-angled one. Blood flows better through arteries that twist gently than through rigid tubes. Curves guide, redirect, and absorb. They keep things moving without interruption. Energy's another key. A straight path might seem efficient at first glance, but in many biological systems, curves do the work better. The coiling of a tendril lets a plant cling to supports without needing stiff, bulky stems. The swirl of a dolphin's fin channels water in smooth vortices, boosting speed and control. Even the arc of a running cheetah's back plays a role. In its incredible stride, flexing and unflexing like a spring in motion. Natural selection doesn't set out to make things curved. It doesn't plan or design in the way we do. But over time, it keeps what works. If a curve helps an animal run faster, grip harder, or survive longer, it gets passed on. If a spiral helps a plant gather light more efficiently or store seeds more compactly, it sticks around. Each tiny advantage accumulates generation by generation, until what remains looks almost sculpted. And sometimes that sculpting is microscopic. Even inside cells, proteins fold in complex curved shapes. These folds aren't random. They're driven by chemistry and physics, shaped by attraction and repulsion. Much like a ribbon curling in water, the exact shape of a protein determines its function. A tiny curve can mean the difference between life and disease. Curves are also great for growth. Spiral, like in a sunflower or a pine cone, lets new parts pack together tightly without overlapping. It's called phyllotaxis, and it shows up in leaves, petals, and seeds. The angle between them, the golden angle, about 137.5 degrees, ensures that each new piece gets the most sunlight, space, and access to resources. No need for instructions. The shape itself does the organizing. You can even see evolution's love of curves in camouflage. Many animals have rounded markings that break up their outlines. Stripes, spots, and swirls help them blend into shadows and branches. A harsh line stands out. A curve disappears. And while nature certainly uses straight segments, think insect, legs, or porcupine quills, it's rarely in isolation. Straight parts are often embedded within curved systems, guided by flexible joints, tapered edges, and circular motion. The line becomes a part of the whole, not the dominant theme. Even in behaviors, curves appear. The flight path of a bird, the swimming motion of a fish, the way a deer bounds through the woods. Few of these movements are linear. Life rarely moves in straight lines. It arcs, adjusts, and flows. That's not just poetic, it's evolutionary logic. Of course, we humans still build straight things. Our houses have right angles. Our roads are engineered with straightaways. But when we design for efficiency and strength, we end up borrowing from nature's playbook. Think of airplane wings, bridges, tunnels, and even sports shoes. Domes, curves, they're everywhere because they work. Evolution doesn't care about aesthetics. It cares about survival. And over billions of years, it has discovered that the gentle curve is often the smartest path forward. Whether it's a tusk, a tail, or a tendril, the arc isn't just elegant, it's earned. And when you see that coil in a ram's horn or that swirl in a fern, you're not just looking at beauty, you're looking at function shaped by time. Nature curves things not because it wants to impress us, but because those curves work. They survive. They stay. In the end, the world we walk through is a gallery of quiet engineering, and everywhere we look, from seashells to skeletons, from petals to paws, the message is curved into the world itself. Life finds the smoothest way. Somewhere along the way, humans looked at the wild, twisting, tangled world around them and reached for a ruler, straight lines, sharp corners, grids on paper. We began drawing our own order onto nature's curves. Perhaps it was an act of control. Perhaps it was convenience. Or perhaps we just found something deeply satisfying in a clean edge and a right angle. Whatever the reason, once we began, we didn't stop. You can see it in how we design cities. Streets laid out like checkerboards, blocks and avenues, rectangular plots of land carved from once winding landscapes. From above, a city looks more like a circuit board than a forest. The organic mesines of hills and rivers gets buried beneath asphalt and grid lines. It makes navigation simple, it streamlines infrastructure, but it also flattens something out of the land. It irons over the irregularity that once made it breathe. You can see it in our buildings too. Our walls are vertical, our floors are flat. Our ceilings meet corners at 90 degrees. That's not because human bodies prefer those shapes. It's because building with straight lines is faster and cheaper. It's easier to stack bricks into rectangles than sculpt them into domes. Modern industrialization made the straight line not just common, but dominant. During the Industrial Revolution, this preference reached new extremes. Machines were designed to produce uniform parts. Efficiency demanded predictability, and predictability favored repetition, symmetry, and straightness. Factories churned out products by the thousands, all shaped for uniformity rather than comfort. Chairs were square, tools were angular. Cities were drawn with rulers. Beauty secondary to order. It wasn't just architecture and infrastructure. It's the mindset seeped into economics, politics, and education. We divided land into rectangles. We sorted people by systems. We trained children to sit in rows, recite facts, and move through life, asterisk, asterisk, asterisk. In straight lines, school, job, retirement. The organic curves of human thought and emotion had to fit inside scheduled boxes. Curves, those symbols of unpredictability, became something to smooth out, not celebrate. Even maps, designed to help us navigate the round earth, flattened and distorted that roundness into neat rectangles. The famous Mercator projection stretched Greenland to the size of Africa and widened the poles into bands, all so that ships could sail in straight lines. It worked for its time, but it left behind a warped impression of the world, one that still colors our perceptions today. But nature, for all our efforts, never stopped curving. Rivers refused to flow in straight lines. Trees kept branching out asymmetrically. Mountains laughed at our grid lines. And slowly, we began to remember what we tried to overwrite. Enter biomimicry. Biomimicry is the practice of learning from nature's designs. Not just for inspiration, but for solutions. Instead of forcing the world into our shapes, it asks, what if we shaped ourselves around the world? Architects began to rediscover curves. They looked at the skeletons of birds, the shells of beetles, the webs of spiders, and saw that nature had solved structural challenges long before we had hammers and blueprints. Curved roofs shed rain better. Arched supports distribute weight more efficiently. Rounded buildings are more aerodynamic and less prone to weathering. The curve returned, not as decoration, but as innovation. Even engineers began to follow suit. Trains and cars became more streamlined. Airplanes took cues from birds and dolphins. Medical devices were designed with the flow of blood in mind, following the same branching geometries as veins and arteries. Technology, once all about hard edges, started to soften. In computer design, early machines were all sharp corners and clunky boxes. But today, the sleekest laptops and phones have rounded edges, not just because they look nice, but because they feel better. Our hands are not made to hold bricks, they're made to cradle curves. In software and digital interfaces, the same trend continues. Rounded buttons, fluid animations, gentle transitions. Designers learned that people respond better to visuals that echo natural forms. The curve calms, the curve guides. The curve feels alive. Even urban planners have started to rethink how we design cities. Walkable neighborhoods with winding paths, green spaces, and curved roads are slowly replacing the rigid, car-centric grids of the past. Roundabouts instead of sharp intersections. parks that follow the contours of rivers rather than resisting them. It's slower, perhaps, but it feels more human. And that's really the heart of it. For all our rulers and compasses, we're not linear creatures. Our thoughts meander, our emotions curve and loop and twist back on themselves. We dream in spirals. We grow in fits and starts. Our hearts don't beat in square waves. They pulse in waves and rhythms, in arcs and echoes. Straight lines can be useful, but they are not the whole story. They're a simplification, a tool, a convenience. Like all tools, they work best when we remember their limitations. The world we tried to straighten is gently reminding us that life doesn't unfold in a sequence of boxes. It curves, it branches, it bends with the wind. And as we move forward, perhaps the best thing we can do isn't to fight that tendency, but to follow it. To let the shapes of our homes, our tools, our cities, and our ideas reflect the quiet logic of nature. Not the forced efficiency of the grid, but the flowing intelligence of the arc. Because while straight lines may be easy to draw, they're rarely the path life chooses. And as it turns out, nature usually knows best. There's something quietly reassuring about a curve. It's soft where corners are sharp, yielding where angles resist. It doesn't rush, it flows. And once you begin to notice it, you see it everywhere. In the arc of the moon's path across the sky, in the gentle loop of a sleeping cat's tail, in the eddies of milk swirling into coffee. The curve is the universe's favorite gesture, a signature drawn across scales from galaxies down to molecules whispered in shapes too vast and too small for us to fully grasp. We tend to think of curves as beautiful, and they are, but they're also practical. Nature is rarely wasteful. A curve, at its heart, is efficient. It guides flow, balances forces, and distributes energy. Arches don't just look graceful, they hold up bridges. Spirals don't just delight the eye. They allow life to grow and expand without changing shape. Every curl and coil in the natural world is doing something, solving a problem, making something easier, stronger, smoother. And this practicality over time becomes elegance. Not the forced elegance of design for its own sake, but the effortless kind. The kind that emerges when things are allowed to be what they are. The kind that results when form follows function, and function flows like water. Take architecture. The most ancient buildings that still stand, the Roman aqueducts, the domes of mosques, the soaring cathedrals, survive because they curve. Arches channel weight down into the earth. Domes distribute pressure evenly across their surface. Builders, long before modern physics, understood this intuitively. They knew that stone prefers the arc to the angle, that a vault endures longer when it mimics the sky. But the universe doesn't wait for architects. Its curves arise on their own. Matter drifts together under the pull of gravity, collapsing into spheres. Planets orbit in ellipses. Stars swirl in galaxies, each one coiling like a giant pinwheel. Even empty space, once thought to be flat and featureless, bends around mass. Gravity is not a force pulling objects along invisible strings. It's the shape of space itself, bowed under the weight of what it holds, and within those curves, everything moves. A photon traveling at the fastest speed nature allows doesn't go straight, not when a star's gravity bends its path. A planet doesn't circle neatly, but spirals slightly, falling and missing over and over, bound by the arc of inertia and attraction. The universe is full of things trying to go straight and failing gloriously. Even light, which we often imagine as the purest straight line, behaves differently. Through water, it bends. Around corners, it diffracts. When it passes through raindrops, it spreads out into a rainbow, a perfect circle, if only the earth didn't get in the way. Curves are not an exception in the behavior of light. They are the rule. At the smallest scales, the curve becomes even more fundamental. Atoms are not tiny billiard balls. Electrons do not march in orbits like planets. They float in clouds and regions of possibility shaped like spheres and petals and toruses. Their positions are described not by coordinates, but by waves. And waves, as any shoreline can tell you, are nothing if not curved. Particles themselves are described by curvature, the very equations that govern their motion triangles. Wave equation, Einstein's field equations, are built from curved relationships. Time and space, energy and mass are woven together in loops and arcs. The straight line, so beloved in classical thought, fades the closer we look. And yet we cling to it, in part because it's simple. A straight line is easy to understand. It has a beginning and an end. It suggests direction and intent, but life doesn't often follow such a path. Our thoughts wander, our stories loop back. Even our lives curve in cycles of sleep and wakefulness, youth and age, learning and forgetting. The arc comforts because it feels more honest. A wave is not lost when it returns to where it began. Spiral is not inefficient because it circles instead of cutting across. There's a rhythm in it, a pulse, the kind you feel when your heart beats, the kind the earth makes as it spins and orbits, the kind your breath makes, in and out, over and over. We used to asterisk, see curves as mysterious. Early astronomers tried desperately to fit the planets into perfect circles, only to find ellipses worked better. Later, physicists thought time flowed straight, only to discover it bends under the weight of gravity. Even now, we often design things in straight lines, grids, charts, schedules only to find real-life loops and weaves. There's something humbling in that. It reminds us that the universe doesn't bend to our expectations, we bend to it. And in doing so, we become part of its rhythm, part of its geometry, not rulers imposed from above, but curves carved by time. Perhaps that's the poetry of it, that something as soft and quiet as a curve could be so powerful that a gentle bend could shape galaxies, guide rivers, define beauty, and dictate the paths of planets and photons alike. That the arc, more than the angle, is what allows the world to hold itself together. Curves are not perfect, but that's just it. They don't need to be. They allow for flexibility, for adaptation, for the unexpected. They make room for flow. So, as we move through this strange, spiraling universe, perhaps we can learn something from its shape. That elegance lies not in the rigidity of the line, but in the gentle strength of the bend. That wisdom doesn't always move straight ahead. Sometimes it loops, wavers, or spirals inward before reaching out again. And in that curve, in that moment of subtle redirection, we find something deeply true, a kind of grace, a kind of peace. Not everything has to be straight to be going somewhere.
Help.
Not everything has to be direct to be meaningful.
Help.
Curve is the point, as we come to the end of our gentle journey. Take a moment to stretch your mind like a spiral unfolding slowly, softly, without edges. We began with a simple idea, that maybe straight lines are less real than we think, less natural, less universal. And now, having floated through galaxies and garden paths, atoms and architecture, shells and shadows, it's hard not to feel that idea settling into place. The straight line, for all its usefulness, is a story we tell ourselves. It's neat. It's predictable. It makes excellent spreadsheets. But when we look at the universe, not just with eyes, but with understanding, we see something different. We see flow. We see spiral arms sweeping through the cosmos. We see rivers meandering, not marching. We see lungs and leaves branching like lightning across sky and skin. We see a world shaped by curves, not conquered by lines. And still we draw. Them we build with rulers. We pave straight roads and sketch maps with right angles. We speak in terms of forward motion, of progress like an arrow. These tools help us navigate, but they do not define the terrain. They are not reality. They're convenience dressed as certainty. Reality, as it turns out, is bendy. It loops. It curls. It folds in ways we're still trying to understand. And yet once you see it, it's everywhere. In the twist of your fingerprint, in the coil of a sleeping pet, the quiet roll of waves in breath, in heartbeat, in thought, even in the way this very sentence may be spiraling through your tired mind. That's a comforting thought, because it means we don't need to travel in straight lines either. We can take our time, can pause, circle back, change course. We can live in spirals, in growth that isn't linear, in stories that wander and return and evolve. It means there's beauty and softness, strength and flexibility, intelligence, in the unexpected bend. So now, as you drift towards sleep or float somewhere between focus and dreaming, perhaps you're noticing the curves around youth, an arc of your ceiling, the shape your blanket makes where it gathers near your knees, the rhythm of your breathing, gentle, cyclical, without a start or an end. Perhaps you're already halfway to dreaming, letting the curves of thought guide you like stars in slow orbit. And before we fade into full silence, let's revisit those questions I asked at the very beginning, questions that now carry a bit more weight, or at least a little more wonder. Where in the world are you listening from? What time is it right now in your little corner of the earth? And how are you feeling here at the end of this curved path? Maybe, just maybe, this was the right shape for tonight. Not a straight shot, but a gentle loop, a wandering arc that brought you somewhere softer than where you began. And if you're still awake, if your eyes are still open, thank you for joining me. If this video helped you relax, helped you learn, or maybe just made you smile once or twice, feel free to leave a like or subscribe. It helps us keep exploring these winding questions together. But if you're already gone, drifting, dreaming, curled like a comma in your sheets, then don't worry. The curves will keep moving even as you sleep, because the universe never stops its gentle dance. It's drawing you forward slowly, lovingly, in arcs and waves. And wherever it leads next, you'll get there one beautiful curve at a time. Asterisk, asterisk, asterisk.